So let's actually talk about these just really quickly since we have a little time. Barrett?
So last time we left off on talking about where you want your frequency to be at.
Yeah.
And we don't want it to be at its very peak efficiency, right?
Yeah, so basically, at these regions, when you switch from one regime to another, that's where you get these losses. Losses, we said, are just heat, right? You're switching this current, trying to do so quickly as possible, but you get regions where you get large losses. So I think the last thing we said last time is that the microwave, when you microwave your food, it's doing this, right? It switches, it picks the region here right next to the one where molecules of water in your food, since most food has water in it, this works really well for food. It picks it and it goes to a slightly lower frequency than the frequency at which these molecules orient themselves, right? Basically, if you take water molecules, and you try and rotate them back and forth, you'll reach a point where they can't rotate any faster than one of these, right? I don't know which one of these it is. I assume maybe this one, right? It's probably this one. So you go right below that. Why would you go right below that? Was I think the last question we raised last time. Any questions? Any thoughts? Maybe turn to a neighbor and brainstorm for a second. Why would you go not right at the peak value, but right below it?
Metal has pretty
Okay, what do you guys think? Why don't we want this peak value? Why do we want just to the side of it? Any thoughts? Yeah, what do you think, Barrett?
Because what I thought is if you're going at too high of a frequency, then it's not going to affect the water molecule, so you want to keep it in a region that it absolutely...
Definitely we don't want to be anywhere over here, because this frequency is way too fast for the molecules to orient themselves. If they can't orient themselves at all, then they generate no heat. You want it to be right at the region where they can kind of orient, right? That sort of frustration, that mismatch, that's what leads to heat, right? So basically, if you're above 10 to the 8th, you're not getting any heat generation from this large contributor, right? So you definitely want to be somewhere between 10 to the 4th and 10 to the 8th. Why do we want to be just to the left of the peak, though? Wouldn't you think, like, put it at the peak, make it, like, maximize your heat generation? Any thoughts why this might not be ideal?
Too much of good things about it.
Too much of a good... Actually, that's true, but why? What's going on? Let's go Barrett and then Sherry.
If you generate too much heat, it could break apart the water molecule.
Okay,
I
Sherry?
was going to say something along the lines of if you just take it to that frequency, it's going to give a really intense event of some sort, which is going to ruin what you're trying to accomplish.
You're all saying the right things. Yeah, Chris?
If you like peak at that frequency, I mean, will all the water molecules be like in perfect synchronous with one another, whereas if you're off of it, they'll actually start like...
Yeah, so the reason they don't do it right at that frequency, it would be correct to say that you would get the most efficient microwave, meaning you put your food in, and for however amount of time it's in there, the amount of heating that occurs would be maximized right at this peak value. However, it will be maximized right at the surface, meaning you've picked a frequency of radiation that basically absorbs the highest amount of heat possible. So the stuff at the surface is absorbing as much of that radiation as possible. The stuff on the inside, somebody said microwave burrito, I heard it somewhere floating, right, is the worst thing ever. Because you nuke a microwave burrito and the outside gets like the temperature of the sun and the inside is like horribly, horribly cold, right? It's terrible. So what you really want is you want your material to be a little bit transparent to the radiation, just a little bit, right? So you pick it a little bit lower so that some of the radiation intentionally goes through into the depth of your food and still is getting some heating events occurring, but you don't want to maximize this. That's the rationale for going just left of this. So let me ask this question. What are these different regimes? Or at least what are some of the different regimes? Maybe the easiest way to answer the question is, at ultra-high frequencies, you're switching this thing fast as possible. What's the only thing that can respond to that? Like, you do have some leftover dielectric constant, right, this thing? What's that coming from? What can respond ultra-quickly that's polarizable? Maybe light. produce a magnetic moment. Polarizable, you're right, I see what you're saying. But it doesn't create an electric field in your material, right? Fair, what's left over?
The separation of the free ion and electron.
Yeah, the electron cloud, right? So if you've got your electron cloud, you've got your nucleus, which is some positive stuff going on here. We've got a bunch of negatives part of our cloud. This is a super overly simplistic drawing, right? We know that clouds have shapes. We've been learning about that, right? But overall, it's sort of this thing that goes around it. At any given moment of time, if you apply an electric field to this thing, you can redraw that cloud like maybe this, right? You applied a field, and very quickly, those electrons can shift a little bit. They call this snapshot dipole, right? Because if you took a snapshot at any given moment of time, it can be shifted, right? So electrons definitely are due to this. Now tell me what these other ones might be due to. What are some things that could also cause polarization? You apply an electric field to a material, and you get charge separation. What's that charge separation coming from? If not from electron clouds getting shifted a little bit. Well, it's water. What's happening in water? When you microwave your food. Yeah, you've got this bent molecule, right? We said it looks like, I think I drew it. Yeah, you've got this thing, and it's rotating, right? So up here, this would be molecular reorientation, right? Rotation of molecules, right? Is that going to be fast or slow? Definitely, it's going to be really slow. You're rotating whole molecules, so that's going to be down here on the slower end, right? Now, what might some of these other events be? What else can cause polarization when you apply a field to something? A whole molecule can rotate. The individual electron cloud can rotate. Anything else that might have a faster response than rotating molecules? Actually, I'm not even sure if this one is rotating molecules. It might be that one. This might be something else. Maybe there's something else that's even slower. Yeah.
Maybe not the whole molecule rotates, but just like the atoms can start vibrating back and forth more.
Yeah, we call this ionic, right? The ionic contribution to it, meaning, so you've got sodium chloride, right? So sodium chloride like that. If I apply a field, basically Megan shifts that way, Chris shifts that way, you shift that way, Sherry shifts that way, right? So you've got your point at which you're supposed to be around, you sort of lean a little bit, right? So leaning for ions, shifting a little bit off position, that's certainly going to be faster than translation, right? Or like this rotation, excuse me, translation, this rotation, right? I actually think this might be rotation, this might be ionic components electron. What might be even slower? I'd have to review my notes from 2010 to be sure of this. Any thoughts to what might be even slower?
Just complete translation.
Yeah, which is diffusion, right? So you apply a field and you've got like a lithium ion or sodium ion, it's literally going to diffuse through the material and create polarization. So I think this might be diffusion. Okay, so that's where we left off last time. Just reviewing stuff we learned about in 2010. The reason we care about dielectric constants is how it relates to capacitors, right? So your capacitor, the capacitance of a capacitor is equal to the permittivity of free space times the area on which you're going to accumulate charge, right? Divided by the separation distance between your two plates, right? So you've got whatever surface area this is, you've got some separation distance, right? If there's nothing between those two plates, if it's vacuum, right, we can calculate pretty accurately how much charge will accumulate on these surfaces just by knowing the surface area and the distance between it. Because this epsilon naught is the permittivity of free space, it's just a constant. Then when you put something inside of there, we said it only gets better. It never gets worse, but it's just a matter of does it get a lot better or a tiny bit better, right? If you put something in there that's easily polarizable and you're talking about a frequency at which you can rotate those things, you could get a really big increase, right? Water, I think, for example, water has a big dipole. It's pretty easy to rotate it. It has it increases it by a factor of k. This is called our dielectric constant, right? So let's say before the amount of capacitance is this. Now it's the same thing plus this factor k, right? So it's literally just like a proportionality constant. And what is that value of k? We call it the dielectric constant. And what are some values that it might have? So here's some typical materials that have been used for a long time, right? You've got like sodium chloride, lithium fluoride, KBr. These are ionic compounds, right? So the ions can shift, so you expect that sort of ionic component to polarizability. But the values you're getting are not huge. You're getting things like between maybe less than 10, right? So even though you've got these ions in there, you're not dramatically increasing the amount of charge you can put on the surfaces using these things. Water, I'm pretty sure, I don't have it on here, I think it's like 80 because it's a polar molecule and you can rotate it. So it's actually quite a bit better than those. Things like, What's that?
Can't have any ions in it, though. Gotta be pure.
Right. What would ions do to it?
Ions would allow charge transfer.
Yeah, it's got to be pure. Actually, so this is like an unknown question. There's a lot of people speculate it. What would the band gap of pure water be? It's a it should be an insulator, right? Pure water. So what would be the band gap? We're actually going to do that experiment in the next 6 months in my lab with Dr. Ricker. I'm pretty excited about it. We're going to try and assess what is the actual band gap of water. Which is neat. Barrett?
For titanium oxide, is that 15 to 170, or is that 150?
That's 15 to 170.
Why is that such a big range?
I'd have to check. Very first thing that comes to mind is, what do we know about TiO2? Anybody know anything interesting about the crystal structure of TiO2?
Is it also monoclinic?
It's rutile, but it's also anatase. There's two different polytypes, just like carbon has like diamond and graphite. So this might be the structures for anatase and rutile. I don't know offhand, but that's the first thing that comes to mind, is that it might be the two different polytypes. I'd have to check. This is straight from his book, this table. All right? So everything looks sort of, whatever, normal, nothing too interesting until you get down here. All of a sudden you get to barium titanate. We're going from, the maximum is maybe 100, 200 for things that they knew for a long time. Like Micah, where's Micah? Right. That was like one of the capacitor materials that they used early on because it was okay, and I think it was maybe 100 or so. All of a sudden, barium titanate comes on the scene, and it's an order of magnitude larger. And then they start finding specific sort of compositions of these, what are called zirconates and titanates, right? Where if you mix different amounts of them, or if you dope it with a little bit of different A-site cations or different B-site cations, so titanium, zirconium, or barium, calcium, strontium, you can get even 2 orders of magnitude larger. So just bonkers, right? This is a crazy amount of additional charge that it lets you put on the surface, right? We basically said if you could put, 1 coulomb of charge on whatever your system is, and then you move to a system that has a dielectric constant of 10,000, you can put 10,000 coulombs instead of 1 coulomb. What does this mean? Does it have any implication? Do we care about this?
Supercapacitors.
Supercapacitors. Tell me what are supercapacitors.
That's a really strong capacitor that you can use in a battery.
Yeah, we had a demo last semester and it didn't work, so we had to watch a YouTube video instead. But this student of mine, actually, I thought he'd be in his class, Harrison. He has these from an uncle or something. He has these supercapacitors where you charge them up, and then when you discharge them, tell me what you think. How quickly can charge come on and off a plate like this? Say compared to a battery. A battery has redox reactions. A redox reaction, you've got like your metal plus picking up an electron to form a metal, and you've got another metal, let's say like B, giving up an electron to form a cation, right? So it's this redox reaction that has to occur to free up your electrons. That's going to be slow, right? Generally speaking, it's going to be pretty slow. This is just electrons piled up on a metal plate. So they are only slowed down by the resistivity of that plate. And if you've made that pretty conductive, which they try to do on these things, you could offload a huge amount of charge very, very quickly. So in the demo, they actually melt like an iron nail, right? They take like an iron or a steel nail, they lay it across the 2 electrodes, so they short it out. That allows all this charge to come flying across from one side to the other, right? And it produces such a large current that actually can melt the nail. So the idea behind supercapacitors is high power applications, something where you need to deliver a high power. They're terrific for that. They're very bad for high energy. It's way easier to store a ton of energy in a bunch of chemical reactions like this, redox reactions. You can make very energy dense batteries that store take your phone, right? This phone, I think it's got like a 30, this one's got a 3,000 milliamp hour battery. That's enormous, right? You couldn't, in that same sort of volume where the battery is on this, you couldn't make a supercapacitor that holds the same amount of energy. But this thing can't deliver that whole 3,000 milliamp hours of capacity anywhere close to as quickly as the supercapacitor, right? So it's not even that one is better than the other technology, it's just that they're different. And in fact, you could probably use these things in tandem. What if you wanted a device that could both deliver power up front pretty rapidly, but then have a store for lower power requirements, but higher energy requirements, right? Anyways, if you wanted to use supercapacitors, you'd want to store as much charge as possible. How could you do that? What would be your strategy if you're trying to pack as much charge on there as possible? Barrett.
Make the surface area as large as you can.
Yeah. C, this is a charge, capacitance, it's going to be proportional to the amount of charge you get on there. It's not a charge, it's proportional to it, right? It is proportional to the surface area and the separation distance. So you'd like to bring these things as close together as you can. If they touch, you've shorted. If you have a bunch of charge and it shorts, you just did the iron nail demo, but in whatever your device is, you don't want that, right? So you want to bring these as close together as you can without any problems. You want to put the biggest dielectric constant material between that gap as possible, right? And then you want big surface area. Anything to watch out for? Is there anything to watch out for? Can we just do this and build up infinite charge on these plates? Yeah.
Arc,
You don't want it to arc. And what causes arcing?
much charge.
Too big of electric field, right? This is E, right? It's the voltage over the distance. This charge building up will be proportional to the voltage. So if you get too big of an electric field, sooner or later you'll get dielectric breakdown. Even materials that are very, very resistant will eventually break down. Alumina will eventually have dielectric breakdown. Yeah, Barrett?
These materials, these dielectric materials, but do they prevent dendrite growth as well? Is that because you have the
Dendrite growth is a different problem. That has to do with something going on with the redox reactions. I don't think we're going to spend time on it in this class. So it does prevent it only because it's in a different category. Dendrite growth doesn't occur in supercapacitors. Okay, so we've got these materials. So maybe a good question to be asking yourself is, what in the world's going on, right? Why do you get 1 order of magnitude, 2 orders of magnitude larger dielectric constant in these materials, right? So, let's see. We'll come back to those in a moment. First off, let me ask you guys, okay, so here's our different sources. Electronic, that means the electron cloud switching. Molecular orientation, that's like the whole thing rotating. Atomic and ionic polarization, that's the shifting, right? If you had to predict the temperature dependence for these different things, what would they be? They go up, would they go down? So Bear, I'm going to skip you because you're answering lots of questions. That's good. I want other people to answer. Let me pick on Thomas.
Well, as temperature goes up, it'll only get worse. I feel like as cooler it is.
So higher temperature, you might get less polarizability.
Yeah.
How come? What's your rationale?
You have like so much energy that it can run out a lot.
So you're right for which one of these? It's wrong for the other one. It's right for one of them.
For polarization and orientation.
This is actually the good one, right? This is what it's for. That helps. That has to do with ionic motion, so it's diffusion based, right? So it actually improves the dielectric constant here. For these ones, it actually reduces it. So basically, imagine you got like preschool, a bunch of little kids, right? If you hop them up on sugar and you've given them a bunch of like energy, so we're doing the same thing with molecules. You give them lots of temperature, give them lots of thermal energy, they're going to rotate and go crazy, right? So it's hard for you to tell them like everyone to this side of the room, everyone to that side of the room, because they're being crazy a little bit. Same thing here. It's less so with here with ionic polarization. It's a little bit tricky, but you can see evidence of it, right? Right here. So here's things that are ionic compounds, right? Here you've got your dielectric constant as a function of temperature, and it's rising. It's becoming a better dielectric with a little bit more ionic mobility, with better diffusion. Meanwhile, things like this, polymers, these things, octane, decane, hexadecane, these are long polymer chains. They achieve polarization by conformations, by rotating, rotating, doing what polymers do. And that, basically, the more thermal energy you give it, it's fighting against entropy, essentially, for that to happen, so it goes down. So you get different temperature dependence depending on which mechanism you're talking about. And electrons don't care. Right? So dielectric strength, this is the resistance to break down under a field. We were just talking about it. So it's volts per unit thickness, that's the electric field. And for things in the book, he gives them weird units of volts per mil. Mil is 1,000th of an inch. We're barbarians, apparently, in this book. So volts per mil, here's some rough values, right? Many ceramics are something like 100 to 400 volts per mil. Rubber could be much higher, 400 to 1,200 volts. That's why when you like work with high electricity, they'll use big rubber gloves, right? Pretty high. Some phenolic resin, this is a thermoset resin. Think of like an epoxy, something like an epoxy, as high as 2,000. And then mica, clay, like these dried out clays that they used to use for old seals and stuff. That can be 5,000, right? So this is very, very good at resisting breakdown, this mica clay, right? But those are some ballpark numbers you can have in mind. Okay, let's talk about dielectric loss. If you're going to store energy in, say, a supercapacitor, right? Or if you're going to use your dielectric material to heat something up, then you may want to dissipate heat with losses, or you may not want to, right? If you're storing power, you don't want to lose heat. But if you're heating up your burrito, then you want to actually lose a lot of heat, right? So you want to have a large dielectric loss. So what do these dielectric losses come from? Well, here's a diagram. Here we're showing voltage versus time. You apply a voltage, and it's like an instantaneous voltage you apply, you hold it for some amount of time, and you drop it, right? Then what would that do to charge? Well, when you apply a voltage, that's going to shuttle electrons and the lack of electrons to the two surfaces, right? So you're going to build up a charge, Q. And you think in an ideal scenario that this would be instantaneous, right? And therefore your current that you observe, the process of moving electrons onto these surfaces, that's your current, right? Electron motion, that's current through the cell. It basically would be like a delta function. You instantly put them on the surface, then it goes down. They're on the surface, nothing's happening, and then they instantly come off when you release the voltage, right? So this is kind of what we expect, right? In the real world, we don't see this. We don't see this instantaneous current. We don't see this instantaneous movement of charge. Instead, we see this. You apply the voltage, just like that, like before. But now you get some current, some charge accumulation, and then it has this time-dependent, you're slowly adding a little bit more charge. And you take it away, and it slowly releases, right? So it's got this exponential rise and decay. Therefore, instead of having a delta function for current, you're slowly tailing off your current, and have another current that slowly tails off, right? So because it has this time component, this is really a differential expression, right? So the expression you talked about, not in our book, but in another common book for ceramics, shown here. So you've got PT, that's the polarization at time t. That's your instantaneous polarization, right? Excuse me. PI is instantaneous polarization. PS is the final value. Tau is a constant, which is your relaxation time, right? So you can write that the difference between your value at a given time and the instantaneous value will be proportional, with respect to time, will be proportional to the difference in your highest value polarization and your minimum. What this really means is that, I wrote it down here, right here. The rate of change of polarization, that's this, is going to be assumed to be proportional to the difference between its final value and its actual value. So basically the biggest difference you're going to get in polarization, the faster it's going to change to get there. If your change is small, it's going to be slow to get there. That's all that means. Now let's talk about loss. Where does loss come from? So in a perfect dielectric, when you apply a voltage, you're going to get a current, and it would be offset by 90 degrees, right? So you apply your voltage here. As you start to apply it, you start to create a current that's lagging. And it's lagging by this phase angle, right, of 90 degrees. Now, when you're drawing these sinusoidal waves, there's lots of mathematical functions that can take into account this sort of sinusoidal shape. What they use is the exponential with an imaginary number, right? So at some point in your math, you would have seen this, right? So the alternating electric field can be written as this. You've got your E naught, that's the maximum value it's going to go to, multiplied by the exponential of I omega t, where omega t, omega is going to tell you basically the rate at which it's switching, right? So you've got an imaginary number in your exponential. That's tricky, but we can use Euler's formula to turn that into things that are easier to deal with, which is sines and cosines. We'll do that in this moment. Anyways, when you have this alternating field, you're going to get a flux density. That's going to be the current that this alternating field causes in your material. But it's not going to be at omega t, it's going to be omega t minus delta. Delta is the loss angle. It's telling you how far this thing's lagging behind. You'd like it to be 90 degrees, but it's often much more than that. More, right? Yeah, you'd like it to be 90, but it's actually more. It can be greater than that. So you're lagging even more. The more that it lags behind, the more heat that must be generated in this process. Barrett?
What are the things that influence the phase angle? And how would we be able to reduce that?
So loss, we'd have to go back up to our initial drawing up here. It basically has to, this is a measure of loss. So in this region, you have your phase angle lagging behind. And what it is, it's just the mechanism can't relate to the rate at which you want your switching to occur at. So it's not a matter of like changing it, I'd say. It's just recognizing different materials are going to have different losses at different frequencies. That's all that means. So you apply a field, it's switching, you create a current, it's also switching, but it's doing so with a loss factor, this delta, right? Let's see. We can use Euler's formula to go from an exponential with this I in it, this imaginary number, into a series of sines and cosines, right? So that's called Euler's formula. And what we've done now is we've got our dielectric constant, and what's great is you've got dielectric constant times cosine delta, and you've got dielectric constant times I sine of delta. So you got these two terms, In the book, they call these K prime and K double prime, and he doesn't go into the math in this book. I can send you a reference to a book that does a better job of it. In the book, his name is Dr. Richardson, he just goes over, he talks about these two constants, says, the ratio of these two things basically tells you what your loss is going to be. You don't want a big difference here. But this is sort of the math behind that. And you'll hear people talk about the loss tangent. All that is, it's the tangent of the loss angle, right? How much further than 90 degrees are you talking about? So this delta value here. And I don't think I'm going to say much more about it. We could talk about what is the actual loss. You can write it in terms of power per cycle, or you can do it power, which is per second. We'll skip that though. I'd rather just have you guys take the takeaway. So the primary criterion for usefulness of a dielectric as an insulator is the loss factor, right? You don't want something to heat up maybe, or maybe you do want it to. Maybe you want a large loss factor or you want a small one, right? To achieve this, you want a low dielectric constant and particularly a very small loss angle. So if you don't want something to heat up, you want a low dielectric constant, and then you want a small loss angle. For applications where high capacitance is still required, then you have to have a high dielectric constant, right? If you have to have high capacitance and you have to have the high dielectric, and in those cases you want to pick the material that has the smallest loss angle possible, right? So there's not much we can do to change this because it just depends on the mechanisms that give you the polarization in the first place. It's rather a better question of material selection, selecting materials that fit the criteria for what you're looking for. Okay. All right, what do we use these things for? We already talked a little bit about it. Energy storage would be one. You build up charge on surfaces and then you release them. Again, this is great for high power. If you want high power application, something where you need to offload or unload charge in a very quick way, this is a great application. Flash bulbs, welders, things like that, they work great for this. Yeah, Chris?
Can you put like a really, really big resistor to slow down the charge rate?
What do you mean? If you wanted to have it not offload quite as quickly?
Yeah, like
Sure. Yeah, you can reduce your current. But, right, so the current won't, trying to think of Kirchhoff's law. What's that? Yeah, you'll be generating heat there. And so I think that you won't actually save total energy. You're still going to be spending energy because you're just going to be heating up your resistor. But your application will see a less of a current. No, current will be the same. They'll see a smaller voltage across it. Yeah, but you can dissipate heat elsewhere. And maybe these things, right? Blocking, they'll use these for blocking. DC current gets blocked, but AC has charge, discharge, current change. This is interesting, right? What do they mean by this? For blocking, a DC current gets blocked. So you've got your capacitor. Capacitor, we don't allow current to go across it, right? So if you apply a voltage, DC voltage, you build up charge, but you don't actually pass current across this, right? Meanwhile, AC will charge and discharge, right? So if you apply DC current, you don't get any current, but AC, where you're switching this back and forth, as these things shuttle off and on, you still get AC current. So this is a device that can allow you to block DC but have AC, right? Which is kind of interesting. There's decoupling, where you use a capacitor to isolate specific voltage in a circuit. Bypass, where you simultaneously block and couple separate AC and DC components. There's filtering. Filtering is interesting. It takes advantage of the frequency dependence of the dielectric constant. So we know that dielectric constants plummet at really high frequencies. So you could engineer that. You could make that. You could use that to your advantage. Or at very low frequencies, right? So they'll have what are called high pass or low pass filters. All that's doing is taking advantage of the frequency at which you can alternate a signal and still get current, right? Something really important that it's done is allowed for miniaturization. The book has an interesting paragraph too on this, where it talks about transistor radios, right? So transistor radios have to have capacitors in them. And currently, the capacitor is 9.5 millimeters in diameter, which is still kind of big. It's yay big, centimeter, right? And that holds 0.05 microfarads of a farad is charge per farad. Per meter squared or per meter? Let's remind ourselves. By the way, there's a link here that talks about the dielectric constant and temperature dependence. This is in the notes. This is interesting. It talks about why it goes up and down. So Thomas, if you had more questions about that. Let's talk about farad though. What is a farad unit? Coulomb per meter, maybe? Let me remind myself what that is. It might be. Okay, it is a coulomb per newton meter. That's not very helpful. A coulomb per volt. Let's look at that one. So over here, so it's for a given voltage you apply it across it, it's telling you, I don't know, charge it or something like that. All right, anyways, so that's not a lot of charge for a given voltage, right? But even that is pretty good because now we have dielectric materials of, you know, really huge. 5,000, for example, something that we can commercially buy off the shelf, no problem today. Back in 1942, so World War II, if you've ever seen them reenact this with their radios, right? It was a guy with a little backpack, right? He had like a little backpack on because he was the radio person. A lot of that was size of these things, right? So they were using titanium dioxide, right? A similar capacitor would have to be 9 centimeters, so now it's that big, right? In diameter. And for the same capacitance, because K is equal to, they're using a value of 80 there. And in 1930, so World War I era, they used mica and a 0.01 microfarad capacitor, 5 times less total charge they're putting in this thing, was 40 centimeters in diameter, right? This is getting like really big. So the fact that we have these crazy high dielectric constants has allowed us to miniaturize electronic packaging in a very big way. And transistor radio is just one example. We could also talk about transistor like MOSFETs. Somebody remind me what a MOSFET looks like? Maybe take an EPS?
Yeah.
So Chris, remind me, what does a MOSFET look like?
Well, you basically have your trenches, but
Okay, you've got your source and your drain. Basically, you're going to have current starting here, and you want it to get to the drain. How does it get there? Why can't it get there first off? What's stopping it? So this is hooked up to wires. Yeah, so let's say that this is like N-type, this is N-type, this is P-type. So if you take electrons from your N-type area, you send them into a P-type area, what's going to happen? They get recombined, right? So like the band diagram looks something like this, right? You've got Fermi level will be constant. N-type means it's going to be close to the top up here. Then it's going to switch up. The P-type region, then it'll go down again. Right, so you've got lots of electrons piled up here, and you've got lots of empty seats, holes basically down here. So if you try and send these electrons this way, they're just going to recombine. They're going to meet up with that hole, recombine, and you get no current going across that. How do we change that? How does a MOSFET work to change that? You put a gate, and how does a gate work? Yeah, you put something that's got to be an insulator. It's critical that this gate, this is the oxide MOSFET, metal oxide, right? Field effect transistor. So you've got oxide right here. I don't even read that at all. That's our oxide, right? What's that doing? Yeah, so up top, you hook this up to a metal contact. So here's your metal oxide semiconductor, MOSFET, metal oxide semiconductor, right? So this would be metal oxide semiconductor. What does this metal up here do? You put a charge to it, and what happens? You put a voltage on this thing. This is a dielectric material, right? It's not going to pass current. If it can't pass current, what will it do instead? It will have an electric field, which will create what? It will create the same thing we're talking about all day long, right? It's a capacitor. You get charge buildup, right? So depending on the polarization that you apply to the top of this thing, you're going to accumulate charge up here and on this backside. And that's what's critical. So let's go back down to this thing. Right? What do you want to do here? Do you want negative or positive building up here? You want negative, because you've already got positive, you got holes, right, in this material intrinsically, or extrinsically, however it's been made. So you want to put holes there, or sorry, electrons there. So you want to put a positive voltage up here, so that you accumulate that, you get a big there. What that does, this creates a channel, a temporary channel. As long as you have a voltage applied from here to the semiconductor, you create a little pathway where electrons can now travel across this thing, right? When you guys take EPS, you'll learn way more about this. This is a quick and dirty explanation, right? But the fact that we now have things like hafnium oxide, which is what they use, hafnium, like that's an element you don't even ever hear about. They use it as the oxide in MOSFETs because it has great dielectric properties, right? It prevents dielectric breakdown, it gets a big charge buildup, right? So these are useful for many, many, many things. This is just one example, okay? So let's talk about why on earth these barium titanate-based ceramics have such enormous dielectric constants. Got 15 minutes. right? We said that most ceramics had certainly less than 100 for the most part. Titanium oxide was interesting because it was higher. All of a sudden, barium titanate rolls up on the scene and it's enormous, right? So the reason it has such high polarization, how about this? Remind your neighbor from 2010. What was the reason it has such high polarization? So, tell your neighbor. Take a stab at it. Okay, let me pick on Jesus. Where's this ginormous polarization coming from?
Is it the titanium?
Is definitely the titanium, right? Everything can contribute, right? If you apply a field to this thing, say going top to top bottom, right? All these atoms can shift a little bit. We know the atoms shift. We've been talking about that, like that leaning back and forth off their position. So everything's going to contribute. It's just that titanium's going to contribute a whole lot more. And why is that? The fact that it's a transition metal, that's not exactly the reason. It's kind of related to it. Barry, you've been answering lots of questions. I'm going to skip you. I know you know it. Let me ask Jake. Like, why does titanium get such a disproportionate role here? You know, it's just one atom. That's part of it. Part number one is that it's 4+, meaning this barium is 2+, oxygen is 2-, titanium is 4+. So it's already, if it moves, you get double the impact because it has twice as much charge. That's the first reason. What's the second reason? There's one more important thing to realize here. Yeah.
Is that like a really small electron cloud that move a lot? Maybe?
Yeah. Think. But when you start to take away electrons, things shrink. By the time you've taken away 4 electrons, it's shrunk like crazy, right? So now you've got a relatively small cation in a pretty big octahedral site, and the site is bigger than it needs to be now, basically, right? So this thing is, imagine you put a golf ball inside something larger than a golf ball size. It's a terrible analogy, right? But like it can rattle around, right? The fact that it can move around a little bit means the displacement, the magnitude of its displacement when it shifts is a lot bigger. So not only it has more charge and it can shift a whole lot more. So let's do the calculation. How do we calculate how much polarization occurs? If this is, you know, when the field is applied, this is what we're seeing. You're seeing the different ions. We're looking down the side of it, right? So here's your A site, B site, oxygens. It's showing you how much shifting has occurred. How do we calculate the polarization here? Back to chemistry. How did you calculate a polarization, a dipole moment? Anybody remember? Okay, you could do it that way. You still, electronegativity is only going to tell you like it's going to tell you how much more of the electron it's stealing away, right? So you really care about the charge. How much charge is it stealing away? Is it a full electron volt? Is it a fraction? Or electron volt? Is it a full charge like a farad? Or Coulomb? Or less, right? So in this case, we're going to take this. We're going to write up a summation. We're going to say the total polarization is equal to the sum over all the things in the series. That was a really bad sum. Right? Over all the atoms in the unit cell, we're going to sum them up. We're going to take the charge, right, that it has, times the displacement. Just charge times displacement. That's all it is, right? So let's do that here. With a neighbor, I want you to figure out, we got 10 minutes left in class, and since we're ahead, let's take some time to actually do this. I want you guys to tell me what percent of the total polarization comes from titanium. What percent? Is it 90%? Is it 10%? Is it 50%? What is it?
Well, there's no fuel drop. So we want to get the percentage. So the charge for that penny, the charge for that. Yeah. So the charge for that penny divided by the charge for that.
Yeah.
So it looks like the oxygen's on the side, it's down low.
Yep, in this case, the oxygens on the side are not moving.
Okay.
The only ones that are moving are the ones in this face and that face.
It's on two oxygens.
So, but remember this is per unit cell. So how many atoms do those actually represent? This is half in, half out. So that's one oxygen basically. So you've got 8 times 1/8. You've got 2 times 1/2. You got titanium. Basically, there's one atom of each type in this exact drawing, right? And you'll see different drawings where it's slightly different.
Would there be more oxygen?
Nope.
Shouldn't be 3.
Well, in the unit cell there are, but these ones aren't moving. If there's no displacement of charge, then there's no polarization. Okay, we'll do 2 more minutes.
How do you know how much they shift? Just through experimentation?
So right here. How do they determine those?
Yeah.
X-ray diffraction. Our old friend. Yeah, you can do site refinement. As you're doing refelt refinement, which Jake spoke to you guys about, you can actually calculate atomic positions and then compare it to structure and refine the atomic position that way. Okay, who's got an answer for me? What fraction of it comes from the titanium itself? Yeah. 9/10? I didn't get the same thing. Anybody else get a different number? Yeah, Bear, what'd you get?
I got 71.2.
That's what I got. I got
The
71%.
absolute value, the oxygen is variable.
Good question. What do we do with the charge here? So this thing, you've got titanium. Oops. So titanium is 4 plus, right? And it shifts up. So let's call up a positive number, right? It shifts up by 0.12 angstroms, right? And we could put in fundamental charge. If you wanted to, instead of writing 4 plus, you could do 4 times 1.602, 10 to the 19. You could turn it into coulombs. I'm just going to skip it because we're doing fraction, right? Then you have to add up the next one, which is barium. That's 2 plus. And it shifts up as well by 0.061 angstroms, right? And then you've got to add the oxygen. Oxygen's 2 minus, right? So it's -2. But it shifts down by 0.036. Oh, it's gone. Why does it do that? That makes me sad. Plus 2 plus 0.061 plus -2 times 0.036, right? So it actually comes out to, they cancel out. Because sorry, that needs to be negative. It shifts down, so we call that negative, right? So overall, if you then take, this is all equal to something, and you divide this by that whole thing, that gives you your 71%. So titanium's doing most of the work here, right? It's disproportionately helping out. The fact that this typically transition metal, things that have relatively high charge, zirconium or titanium are the 2 most common, really improves the dielectric constant that you get out of this. So clearly, you have to have a material that looks kind of like a perovskite, right? This is the perovskite structure, right? However, in class, like 2010 and earlier in this semester, we talked about perovskite as being totally cubic, like this, right? This thing's right dead center. These things are centered on those corners. We did not draw it where those things are shifted up. This thing's shifted. The oxygens are skewampus, right? That changes the crystal structure, right? So in fact, there must be a transition, a transformation from cubic to what crystal structure? What crystal type of system is this? It's no longer cubic because things have been shifted vertically. So this parameter A and this A, they're still the same, but this is now longer, which makes it a what type of crystal? Tetragonal. So it goes from cubic to tetragonal. If you go lower, still actually goes to orthorhombic, meaning these are no longer the same value either. So there's a temperature at which that occurs. Like thermodynamics tells us when these things happen, right? Remember the phase diagrams? You could find it on the phase diagram, and above it would say C or something, and below it would say T, cubic to tetragonal, right? So free energy is the reason here, right? We've already talked about what dictates free energy in the system. But it's important for you guys to remember is that low temperature, high temperature. What do you expect to happen to the dielectric constant as you go from low temperature to high temperature? Same exact material. You don't change the material at all, you just heat it up. Thomas, what happens?
Since they expand, right, it'll have less more polarization.
Which one has more polarization though?
The one you have to use the triangle.
This has a whole lot more polarization, and this is the low temperature phase. So you heat this thing up, what happens?
Then it won't go lower than right.
Your capacitor disappears, right? Your thing that had like 10,000, right? What units of this? Oh, it's unitless, it's dielectric constant. Goes from 10,000 back down to, I don't know, 10, whatever this value is. Way, way lower, right? So these things are great, but it's important to recognize that this is contingent upon whatever phase you're in, and phases depend on free energy, therefore there's this temperature component to them. Yeah, Barrett?
So with the heat loss, I think then in this case, we extremely detrimental.
Would heat loss be really detrimental? So if you generated a lot of heat and you heated this up above this temperature called the Curie temperature, then that would be really detrimental. But then interestingly, once it heats up, it no longer has a large dielectric constant, and your heat loss would plummet. And so it would self-regulate, it would go back down in temperature, because it would no longer be a good dielectric, which is kind of interesting. Jake?
So if you're using like this little capacitor and just like in theory, if the plate that you were using with this as a dielectric had the significant resistance, how would that affect like because we would get some heat generated from it really bad?
Can you say that question one more time? I don't
So
think I
like,
heard the
imagine
beginning.
you were using this just as a dielectric and then you had like a your capacitor on top.
Oh, okay, the metal plating on top of it.
So
Okay,
that
yeah.
have, like any significant resistance where when you're using the charge on this capacitor, like as that heats up, would it just
We could calculate it, right? We could calculate this. We could figure out how thick is that. Maybe we should make a homework question out. We'll say, nobody blame Jake. This is a good question, right? But like we could say to shuttle on this amount of charge in this amount of time. That's a power, right? You know the current that must go into that. If you know the resistivity of that metal, you could then calculate the power and therefore the energy dissipated. If you know that energy had to go somewhere, you're going to heat up the metal electrode plus maybe the dielectric by it. You could do the calculation, right? And it would just depend, like system to system. It may matter, it may not. Depends on how close you are to the Curie temperature. Interesting question. Okay, we'll pick up here next time.